So yesterday we have seen the product of two primitive polynomials is again a primitive polynomial. So let me define a new term. Let's say B bearing and AB a subring of B. So when I'm saying subring of B, so I mean ke both have the same multiplicative identity, right? I mean, besides subring, because we are dealing in context of fields, right? So this is what when I'm saying subring, so I mean A is a ring under the same operations as that of B, and besides this, I mean A will have the same multiplicative identity. Okay, so then A is said to be inert in B. If for any C in B, so you have an element in B, any element in B, uh, having factorization in B, so that means no, sorry, C is an element in A. So for any element in A such that it has factorization in B, that means C equals A dot B for some AB in B. That means you have an element in A, any element in A have factorization in B, then there exists a unit U in B such that A dot U and U inverse dot B, these are elements in A. So that means what is happening? Any element in A have factorization in B, then this factorization you can pull down to a factorization in A via unit. क्योंकि ये अभी factorization C, you can say that C is same as A U dot U inverse B, और ये factorization अभी कहाँ पर है? A में, because AU in A, U inverse B in A, right? So A is said to be inert in B if for any element in A having factorization in B, then you also have a factorization in A. Is that fine? So this simply means every factorization of C in B can be pulled down to A. That simply means if an element is unfactorable in A, it remains unfactorable in B. If C is unfactorable in A, it remains unfactorable in B. क्योंकि अगर अनफैक्टरेबल है ए में, बी के ऊपर फैक्टरेबल हो गया, तो दैट फैक्टराइजेशन यू कैन पुल डाउन टू अ फैक्टराइजेशन इन ए, right? So in particular, if it is unfactorable in A, it remains unfactorable in B. So got the definition?
Yes,
Yes.
sir.
Okay. So this next theorem will give you a class of inert subrings. So let's say A be a UFD, unique factorization domain with field of fractions K. That means quotient field is K. Then the polynomial ring in X over A is inert in polynomial ring in X over K. So then AX is inert in KX. Alright, so this will give you a class of subrings which are inert in its superrings. So uh, let's see the proof. So A AF UFD, it's given to you. You want to show that AX is inert in KX. So start with an element in AX. So let's say F, any element in AX. And suppose it has factorization in KX. Because what I want to show, any element in AX having factorization in KX must have a factorization in AX too. Right? That's what I'm looking for. So suppose fx has a factorization in kx. This is for some gx hx in kx. So fine. Now k is the quotient field of A, right? तो quotient field में basically if you recall what are the elements? K में elements कैसे होते हैं? A mod B type के where A B are in A and B is not zero, right? And you know, I mean, it represents a class. A mod B represents a class, equivalence class. Is that fine? Because the same element A mod B may be equal to CA mod CB for all C in non-zero in A. So this representation is not unique. All right. So Gx coefficients of G and H are coming from K, and you are working over a unique factorization domain. So fine. So what you do by taking common denominator, I mean by taking common denominator or by multiplying common denominator to Gx, let's say if alpha is a common denominator, then alpha dot Gx will be a polynomial in A. Is that fine? Are you getting?
Yes, sir.
I mean, it's like, I mean, you take the LCM of all the denominators, least common multiple of all the denominators, right? So if alpha is the LCM of all the coefficients of fx, then alpha dot fx will be a polynomial in ax. Is that fine? Let's say fx is maybe some ai bi dot xi, and let's say maybe I from 0 to n. Maybe let's say alpha is the LCM of b0, b1, b2, bn. Then alpha dot fx, basically it's a polynomial in ax, right? So that's what I'm going to do by taking common denominators, or what you call LCM of denominator of coefficients of gx. uh, there exists alpha naught where in A, such that alpha naught dot gx is a polynomial in ax. Fine. So the problem is कि अभी alpha naught dot gx, it may not be a primitive polynomial, will not be a primitive polynomial. So what you can do now, take the GCD d of all the coefficients of alpha naught gx, right? And then divide by the GCD. So now divide by GCD of coefficients of alpha naught g. So let's say g1x will be alpha naught mod d into gx. Now this is a primitive polynomial in ax. Is that fine? Is this all right to you? क्योंकि जो GCD था उससे आपने डिवाइड कर दिया, जो भी ग्रेटेस्ट कॉमन डिवाइजर था उससे आपने डिवाइड कर दिया. सो GCD अभी तो 1 ही रह जाएगा फिर.
Yes, sir.
Okay. So let's call this alpha naught mod d as alpha. So where alpha is alpha naught mod d, and it's an element in uh, a sorry, k. It's an element in k. All right. Because alpha naught coming from a, d coming from a, so this quotient will come from k. So the same thing we can do with h. So similarly, there exists beta in k such that h1x equals beta dot hx, and this is in ax. रिमेंबर ये अभी पॉलिनोमियल ax माने ax पे है, राइट? ऊपर लिखा हुआ है, दैट्स फाइन. So, and where h1x is primitive. All right. So alpha भी k में, beta भी k में, so alpha beta will be an element in k. So k में element तो किस टाइप का होता है? Alpha beta will be of the form sum a mod b for sum a b in a, and of course b is not zero. So that means a by b into fx, this is same as alpha beta fx, this is same as g1x into basically alpha dot alpha dot gx into beta dot hx, which is g1x into h1x. So that simply means this gives you a dot fx, it is b dot g1x into h1x. Now what I claim is that a must be unit. Suppose not, because a is a UFD, unique factorization domain. So if it is not unit, it must be a product of primes. So if it is not unit, you must have some prime. Divide say, if a is not unit, then there exists a prime p in a such that p divides a. Now p divides, oh, one thing, I can add the assumption here, alpha beta is a mod b, and where I can assume that this is the simplest form, that means GCD of AB is 1, this is what I can assume. GCD of AB is 1. Alright, so p divides a, so this means p divides a dot fx, so p divides this side, b dot g1x h1x, and p is relatively prime to b because GCD of a and b is 1, right? As GCD of ab is 1, p must divide g1x into h1x, and this simply means the product is not primitive. But this contradicts the yesterday's result that product of two primitive is primitive. Over a UFD, product of two primitive is primitive. And this contradiction because you said that you have some prime divides A. So that means A must be unit. So this means A is unit. Now go back to alpha beta. Alpha beta था आपका, this is A by B, so that simply means that is A equals B alpha beta, right? So this is a unit in A, is a unit. All right. So fine. So all right, this is a unit. So what you do? Hmm, fine. So this, अच्छा ये B एलिमेंट कहाँ पर है? B is in A. Alpha, where is alpha? If you recall, ये जो alpha था, what was alpha?
Okay.
Yeah, alpha in K. All right. So fine. Now what you do? Hmm, alpha dot gx. This is in already in AX. Is that fine? पहले से ही है alpha dot gx, तो g1x हो गया ना. Now what is alpha inverse h? Alpha inverse hx is same as, you can write, because A is invertible. So A dot it's sorry, A inverse dot B beta hx. Is that fine? All right. Basically A is unit, so आप इसका दोनों तरफ यूनिट इस्तेमाल करो. So alpha inverse will be A inverse, let's say B beta, right? Is that fine?
Yes, sir.
Now look at this. Beta dot hx, where it is? It's an this is A inverse B h1x. Beta dot hx तो h1x था ना. तो ये है ax में, ये प्रोडक्ट भी hx में गया. A इनवर्स यूनिट है A में, तो ये भी hx में गया, तो ये भी ax में आ गया. Is that fine? So go back to the definition. I was looking for a unit element in K such that alpha dot gx is an element in AX, alpha inverse dot hx is an element in AX, and तो ये फैक्टराइजेशन हो गया. fx is gx dot alpha inverse, it's an element in AX, alpha, sorry, gx dot alpha. Alpha inverse dot hx. Alpha is the element in K ये ए में आया, ये भी ए में आ गया. So I started with an element in ax, assumed it has a factorization in kx, and that factorization I pulled to a factorization in ax. So that means ax is inert in kx. That's what I wanted to show. Is that fine? Any doubts so far? Yes? Any doubts so far? Okay, so I'm assuming no doubt. Am I audible?
Yes, sir.
Okay, fine. So, all right. So let me uh, give you a definition, new definition. A group G, basically these are something related to group theory, but because we will use, so that is why I am giving you here. So a group G is said to have finite exponent if there exists a natural number n such that x power n is 1 for all n for all x in G. So naturally I am assuming कि multiplicative group है. Is that fine? अगर कुछ confusion हो तो आप लिख सकते हो. It's a multiplicative group. All right. So if G has finite exponent, then the least such natural number n is called the exponent of G. Least such n is called the exponent of G. All right. So you know if assume G is a finite multiplicative group, finite abelian group. So naturally, I mean from the definition of exponent, every finite group will be a finite exponent. Is that fine by Lagrange's
Yes,
or one of the application of Lagrange's? So assume G is finite abelian multiplicative group. Then you know if G has an element of order m, if it has an element of order n, then it will also have an element of order LCM of m and n. So basically, if G has an element of order n and an element of order n, then G also have an element of order LCM of m and n. Alright, so let's see a quick proof of this. Though many of you may be aware. अगर सबको पता हो तो I think I can skip the proof. चलो देख लेते हैं. First, let's establish this. First, assume the case when m and n are relatively prime. So in this case, order of AB. That's basically order of AB will be the m and m dot n. So suppose order of AB is what you want to call K. Then K will be less than equal mn, as AB whole power mn will be 1, because we are dealing with abelian groups, right? So K will be less than equal mn, that's one thing. On the other side, what you do, if AB power K dot m. Okay, I think let's assume order of A is what you want to call m, order of B is n, and AB are in G, and GCD of m and n is 1. All right. So order of A is m. So A B power km. This is B power km, and because order of AB is k, so this is 1. Fine. So that simply means the order of B is n and B power km is 1. So order will divide km. That means n will divide km. N is relatively prime with m. So that simply means n has to divide k. And by the same logic, you can conclude that m also divides k. And because GCD of m and n is 1, so m divides k, n divides k, this simply means mn divides k, as GCD is 1. So that means you have the other way. So that is equality. Now suppose, I mean, they are not relatively prime. So let's say what you want to call GCD is not 1. All right. So what you do, let's say LCM may be K. Put K to be the LCM of M and N, and let's its prime factorization is maybe P power P1 alpha 1 P2 alpha 2, maybe what you want to call Ps alpha s. It's a prime factorization of k. All right. To p1 power alpha 1, what you do, p1 power alpha 1, because it's the LCM of m and n. So either it will divide m or it will divide n. Is that fine? क्योंकि एलसीएम को डिवाइड कर रहा है तो दोनों में से एक को तो डिवाइड करेगा. So if it divides m, then you have an element. Basically, what is that? So basically आपको चाहिए था एलिमेंट p1 पावर अल्फा 1 का, राइट? सो basically it's divide, so maybe p1 alpha 1 into something, what you want to call, let's say q is m. So what is the, which element will have the order a power m mod q? Its order will be p1 p1 alpha 1. Is that fine? Is this all right? Are you getting the point? Is that fine? Basically what is happening, m mod q and the m, they has to be relatively prime.
Sir, can't we proceed with AB here also?
I mean, there may, I mean, if you have that proof, then that's fine. There may be many proofs, right? I'm giving you just a
Yes, sir.
quick idea. Okay. So the, by exactly the same logic, similarly, you will have an element of order pi alpha I for all I. Similarly, there exists an element of order pi alpha I for all I, right? So now you can use, so you have an element of order p1 alpha 1, you have an element of order p2 alpha 2, both are relatively prime, so you have an element of order p1 alpha 2, p2 alpha 2, right, and so on. So by case 1 you have an element of order p1 alpha 1, p2 alpha 2, and so on. P, what is that? S alpha s. Okay. So the point is, if G has an element of order m, if it has an element of order n, then it will have an order element of order LCM of m and n. All right. So one more lemma. Let's say G be a finite abelian multiplicative group, and n is the element maximum of order of A for all A in G, right? So then this number n will be the exponent of G. That's what I want to show. N is the exponent of G. That is, so because this, I mean, if you look at this, n is the maximum of order of A for all A in G, that means you have an element of order n in G. Is that fine? So that means suppose A is that element, order of A is n. तो exponent n से छोटा तो नहीं हो सकता, because A power m cannot be equal to 1 for all m strictly less than n. Is that fine? So naturally, if I prove that x power n is 1 for all x in G, then this n will be the least such. So it is enough to prove that x power n is 1 for all x in G, as the exponent of G cannot be less than n. So enough to prove this. Once I establish this, this n will be the least such. Alright. So let's say A be an element in G and order of A is n. Suppose there exists an element B in G such that B power n is not 1. If this is not 1, naturally order of B cannot divide n. This simply means order of B cannot divide n, क्योंकि अगर B को n को divide कर देगा तो फिर तो B power n has to be 1. Is that fine?
Yes, sir.
So that's simple. Let's say order of B is n. Order of B is m. What can you say about LCM of m and n? Because this order of B can, this m cannot divide n. So can I say this will be strictly bigger than n? Is that fine? If m do not divides n, then LCM will definitely be bigger than n.
Yes, sir.
So that, but then the point is, in the previous lemma, we proved that if it has an element of order m, if it has an element of order n, then it will also have an element of order their LCM of m and n. So this means G has an element of order LCM of m and this is strictly bigger than n, but this violates the definition of n. What was the definition of n? Definition says that n is the maximum of order of all the elements, right? So you are getting contradiction. You are getting contradiction because you said that if possible you have such an element. So that means no such element will exist. All right, so this gives you one more thing. Exponent in case of finite abelian group, exponent will be the maximum of order of all the elements of that group. All right, so come back to the field theory now. In any field F, the roots of the equation x power n equals 1, this is for any natural number n, forms a multiplicative cyclic group whose order is a divisor of n. Is that fine? So you pick the, consider the, in any field, consider this equation xn equals 1. Now consider all the elements in F which satisfy this equation. That means basically you are looking all nth root of unity in any field F. Okay? So naturally that this the set of all nth root of unity in any field forms a multiplicative group. That's quite clear. Is that fine? Let's say G be the set of all the roots of xn minus 1 equals 0 in F. F is the any given field. So naturally this G is closed under multiplication. I mean G is a multiplicative finite multiplicative group. Is that fine? G is a finite multiplicative abelian group naturally, क्योंकि फील्ड में तो मल्टीप्लिकेशन अबेलियन है ही. Is this fine? As if alpha beta in G, that simply means alpha n is 1, beta power n is 1, so you have alpha beta whole power n is also 1. Is that fine? Alpha beta inverse is also 1. Is that fine? Simple? Okay, so go back to the statement. In any field, the roots of this equation forms a so multiplicative group. That's fine. And so the big thing is cyclic. I want this cyclic group. Okay. And whose order is a divisor of n. That's another thing. Right? क्योंकि जरूरी नहीं है ये इक्वेशन f के ऊपर सेपरेबल हो, तो जरूरी नहीं है कि सारे के सारे रूट्स f में हो इस पॉलिनोमियल के. इस इक्वेशन के सारे रूट्स f में हो जरूरी नहीं है. इट मे नॉट बी सेपरेबल. यू मे हैव रिपीटेड रूट एज वेल. So okay, so G is finite multiplicative abelian group. That's fine. So let's तो finite है तो इसका कुछ exponent होगा. G will be a finite exponent. So let's say this gamma is the exponent of G. Fine. So basically, as you have seen in the last lemma, the maximum of order of all the elements in G, it will be gamma, right? Gamma will be the maximum of order of all the elements. So basically, you will have an element in G of order gamma, right? So then x power gamma is 1 for all x in G, and G has an element, say A of order gamma. All right, that is order of gamma is n. So one thing, order of gamma is n. Sorry, what I'm saying. Order of A is n. Sorry, order of A is gamma. Let me correct. Order of A is gamma. So order of A is gamma. A कहाँ पे है? G में. A G में है तो A will satisfy this equation x power n equals 1. So as A power n is 1, so that means A will, so what you have is this gamma must divide n. The order of A will divide n. Is that fine? ठीक है. And by Lagrange's, order of an element divides the order of the group as well. So gamma will divide order of G as well. So basically what I will show that the order of G is gamma. That's what I will show. So gamma divides n. This is so gamma is order of G. Order of G divides n. So this will complete the proof. All right. So now you have two things. One, gamma divides n. Number two, gamma divides order of G. So what you do, consider the equation x power gamma equals 1 over f. ठीक है. Any polynomial of degree n will have at the most n roots in any field. Fundamental theorem, right? तो ये इक्वेशन है, it is of degree gamma, so it will have at the most gamma roots in f. Is that fine?
Yes,
And gamma roots you already have in your hand, because every element of G will satisfy this equation. Every element of G will satisfy this equation. This is what. Right? So it will have, so the equation as the above equation can have at most gamma roots, and order of G roots we already have in our hand, because every element of G satisfies this. Order of G roots uh, we have. or we already have. So what's the conclusion? Order of G will be less than equal gamma. Is that fine? देखो यहाँ से आएगा gamma divides order of G, that is gamma must be less than equal order of G. Now look at this. So equation can have at the most gamma roots, but every element of G satisfy this equation. So that means के order of G roots तो आपके पास हैं ही already, और upper bound है gamma की. So order of G will be less than equal gamma. So when you club both, this means order of G is exactly gamma. So this set completes the proof. I think I have proved everything. Order of G is gamma. G has an element of order gamma. That means G is cyclic. Right? And gamma divides n. So, gamma divides n. This one. So I think I have proved all the things. Look at this statement. Cyclic group, order of G divides n. Is this all right? Yes.
Yes, sir.
So as an immediate corollary to this, I'm leaving as an exercise to you. Otherwise, we'll discuss tomorrow. As an immediate corollary to this, you can easily see that for any finite field, so field is finite, right? So finite field means field with finite number of elements. So for any finite field, K star is the set of all non-zero elements, forms a multiplicative cyclic group. This I'm leaving as an exercise to you. If you do, it's fine. Otherwise, we'll discuss tomorrow. So anything from today's lecture? Yes? Okay, in case no doubt, I'm leaving now. We'll meet tomorrow at the same time.